Hi everyone, welcome back to MATA35. This is lecture 9C. In the very last lecture, 9B, we gave a brief introduction to complex numbers and how they represent rotations. And that's where we're going to get started today, which is we're going to remind you all that, again, complex numbers represent rotations. And this is super important because what we'll find is that, remember, a lot of our solutions to the ordinary differential equations came in the form of e to the lambda x. Like that was how our solutions looked. And what we'll see is that sometimes those eigenvalues, so those roots of the characteristic polynomial, are complex. And in that case, we'll have to use Euler's formula to figure out what real solutions you can get out of them. So let's make that a bit more obvious with an example. So consider the equation y double prime plus y is equal to 0. And we're going to use Euler's formula, so I'm going to put that here. And let's try solving this differential equation. So when we solve this differential equation, the first thing we'll say is, well, we want the characteristic polynomial to be equal to 0. So that's lambda squared plus 1 is equal to 0. Well, when you do that, you find that lambda is equal to plus or minus the square root of minus 1, so it's equal to plus or minus I. Now we have two different eigenvalues, two different roots, and so we therefore know that a general solution to y is equal to c1 e to the ix plus c2 e to the minus ix. Now there's a bit of an issue here though, right? Which is that we started with a real differential equation, and ideally we want a real solution. But this formula for y, this is not real. So how do we get a real solution instead to y instead of this complex solution? And to answer that, what we'll notice is that e to the ix, well, that's equal to cosine x plus I sine x. And e to the minus ix is equal to cosine of minus x plus I sine of minus x. But of course, cosine is even, so that's equal to cosine of x. And sine is odd, so that's minus I sine x. Why does it become lambda squared? Oh, because we had two derivatives here. So it's y double prime. So that's why you had the lambda squared. So the number of derivatives is the power of the of lambda in the characteristic polynomial. Okay, but now we can use those formulas and substitute things in. So then y is going to be equal to c1 cosine x plus I times c1 sine of x plus c2 cosine x minus I times c2 sine x. So now all we're doing is we're plugging in the values for e to the ix and e to the minus ix. Well, you can combine together these coefficients and you get y is equal to c1 plus c2 times cosine x. Y is equal to c1 plus, c2 cosine x plus I times c1 minus c2 sine x. But of course, we can combine together coefficients. So another way of writing this is that you have y is equal to, I'm going to call this c1 hat because it's just the different c1, cosine x plus c2 hat sine x, where c1 hat is equal to c1 plus c2, and c2 hat is equal to I times c1 minus c2. And so what we did is we started, and of course if you choose these two, c1 and c2 hat, to be real, then you end up with a real solution. So even though we started out with a complex solution, c1 e to the ix plus c2 e to the minus ix, we end up with we can restrict it down to a solution that's just purely real. So some constant times c cosine of x plus some constant times sine of x. Okay. Let's give another example because this is a little bit tricky to understand. So y double prime plus 2y prime plus 5y is equal to 0. So again, the first thing you do is you write out the characteristic polynomial. Lambda squared plus 2 lambda plus 5 is equal to 0. And therefore, by the quadratic formula, lambda is equal to minus 2 plus or minus the square root of 4 minus 20 over 2. When you solve this all out, this ends up being minus 1 plus or minus 2i. And therefore, you can solve this, and you know that y, the general solution to y is equal to c1 e to the minus 1 plus 2i times x plus some other constant times e to the minus 1 minus 2i times x. And that's because we had two independent solutions, right? So we another way of thinking about it is we had two different solutions, e to the minus 1 plus 2ix and e to the minus 1 minus 2ix. But what if we could come up with two other solutions? And so that's the other way of thinking about this, which is, well, we have e to the minus 1 plus 2ix is equal to e to the minus x times cosine 2x plus I sine 2x. And we have e to the minus 1 minus 2i x is equal to e to the minus x times cosine 2x minus I sine 2x. And one thing you'll notice is if you combine together these two solutions, e to the minus x cosine 2x and e to the minus x sine 2x are also independent solutions. Right? And so another way of doing it is you can instead write y is equal to some constant. Let's call this c1 hat, just so that we can distinguish it from the other one, but it doesn't really matter because they're just constants. Yeah, I will repeat both these slides slower again on the next one again. So I'm explaining this in three different ways. So hopefully one of the three will stick. So this here is some constant. Let's call it c1 hat e to the minus x cosine 2x plus some other constant c2 hat e to the minus x sine 2x. Okay, which is basically the same as on this previous one, where you had instead of using e to the ix and e to the minus ix, you combine together cosine of x and sine of x. Here, instead, we're combining together e to the minus x cosine 2x and e to the minus x sine 2x. So basically what we're doing is we're taking these complex exponentials, we're breaking them apart into two different pieces, and then we're using those two pieces as the independent solutions we're combining together to get a general solution. And let me summarize this all together on the next slide, which is complex roots of a real polynomial always come in pairs a plus or minus ib. This is just a fact. If a characteristic equation of an ODE has roots a plus or minus ib, then we get these complex solutions. E to the a plus ib times x and e to the a minus ib times x. Okay? Alternately, it has real roots e to the ax sine bx and e to the ax cosine bx. And what we did on these previous two slides is we gave examples of how we could justify this solution. And so therefore, when you're actually solving these things, these problems, for example, if I had y double prime, let's see, what did I do for this one? Y double prime minus 2y prime plus 10y is equal to 0. So the characteristic equation is lambda squared minus 2 lambda plus 10 is equal to 0. Lambda is equal to 2 plus or minus the square root of 4 minus 40 over 2, which is equal to 1 plus or minus the square root of minus 9, which is equal to 1 plus or minus 3i. Okay, so we all understand, hopefully, and you should stop me if this isn't true, but hopefully we understand that we can solve for lambda, and that gives us some complex value, right? The point of this slide is that you can immediately go from those complex values to a real set of solutions. So obviously you can go to the complex set of solutions, which are here. But if I ask you for a real set of solutions, you can also immediately go to it by using the red thing. And so then y is equal to c1 e to the x sine 3x plus c2 e to the x cosine 3x. Okay? Because this here is of this form. So if you get roots of that form, you can immediately jump to the sine and cosine solution. And the reason for it is because you can take linear combinations of the sines and cosines, and you get the complex exponential. Can you explain the last part in red again? Yeah, so basically, the whole point of the slide is that we have this formula if we have the roots that are in this form, a plus or minus ib. And here, we found roots of the form a plus or minus ib, right? So once we've done that, you can immediately jump to, to the solution in red. Because you have two different real solutions, and you just take linear combinations of them. So C1 times one of them plus C2 times the other one. Okay, so let's try this out. So let y double prime plus 4y prime plus 29y equal 0. Which of the following are solutions to the ODE? And I have a couple different solutions here. Oh yeah, and then you add them, yes, because that's the whole point, right? When you have the different independent solutions, you can add together linear combinations of them. So which of these are solutions to the ODE? And the first thing you have to do, of course, is you need to solve for the roots. So lambda squared plus 4y plus 29y is equal to 0. You need to solve for lambda. Oh, let me reset the chat before you guys answer. And of course, we know how to solve this. I'm going to use completing the square. So this is lambda plus 2 squared plus 25 is equal to, I wrote that out badly. Plus 4 lambda plus 29. There. And so therefore you have lambda plus 2 squared is equal to minus 25. Lambda plus 2 is equal to plus or minus 5. Oh, I keep on jumping onto the wrong slide here. Is equal to plus or minus 5i. And so lambda is equal to minus 2 plus or minus 5i. So which of the following are solutions? Okay, so we have a couple A's, we have a C. Okay, so let me actually go through and solve this out. So what are the different independent solutions? Well, we have e to the minus 2 plus 5i x. We have e to the minus 2 minus 5i x. We also have e to the minus 2x cosine 5x and e to the minus 2x sine 5x. And one of the things you'll notice is that the correct answer here is actually C, all of the above. Because these are all like variants on these two. So the first one is obvious. The second one, if you combine together the two exponents, you get minus 2 plus, yeah, so yes, D. Yep, thanks for the catch. The answer here is D. It's all of the above. Because all of these are just slightly different ways of writing solutions of this form. Okay, and let me go ahead and ask the next part, which I think Samantha already like glommed onto. What about real solutions? Which of these are real solutions to the ODE? So things that don't have any imaginary numbers. Yep. So the answer here is indeed C, because C doesn't have any imaginary numbers in it. It's just completely real. So even though some of our solutions have imaginary numbers, we can pick solutions that only have real numbers. Oh, can I show how B is a solution? Yes, I can. That's a very good point. So let me give myself a little bit of space, actually. So what is B? So minus pi e to the minus 2x e to the 5ix, right? So this is equal to minus pi times e to the minus 2x plus 5ix. Because when you multiply together two different exponentials, you just add together with the same base, you add together their exponents. And so this is equal to minus pi e to the minus 2 plus 5i times x. And of course, that is the correct form. Okay. Next. So, like real roots, like repeated real roots, if a plus or minus bi have multiplicity k, then you just have to add an extra x onto the front. So let me give an example, which is if you have y quadruple prime, that's 4 of them. Hopefully you guys can see you guys can see those marks. Plus 4y double prime plus 4y is equal to 0. Well, then what we're left with is the characteristic polynomial, lambda to the fourth plus 4 lambda squared plus 4 is equal to 0. And therefore, lambda squared plus 2 squared is actually, let me change this slightly. I'm going to modify this problem on the fly so I don't have to deal with too many. Let's do what's going to work? Let's do 8y double prime plus 16y is equal to 0. So I'm just changing up the numbers to make the numbers work out a bit more nicely. So we have lambda to the fourth plus 8 lambda squared plus 16 is equal to 0. So this is lambda squared plus 4 squared is equal to 0, right? So therefore, we have lambda squared is equal to minus 4. So lambda is equal to plus or minus 2i. But multiplicity 2 on each of them. This is because you can rewrite this as lambda plus 2i squared lambda minus 2i squared is equal to 0. And this means that the final solution is going to be y is equal to c1 cosine of 2x plus c2 sine 2x plus c3 x cosine 2x plus c4 x sine 2x. So basically, if you have a higher multiplicity, again, like with the real roots, you just add an x in front of your solution. So let's give a brief summary of what we've done. So to solve a linear nth order homogeneous ODE, you construct the characteristic equation. The n roots counting multiplicity of the characteristic equation, they're either real, so we either have real roots or we have complex conjugate pairs. If lambda is a root, real or complex of multiplicity k, then you have e to the lambda x, and if you have it multiple times, then you have x e to the lambda x all the way through x to the k minus 1 e to the lambda x. Those are all solutions. If you have a complex conjugate pair, so this is a conjugate pair is when you have a plus or minus ib. Then and each of these is of multiplicity k, then you have e to the ax cosine bx, x e to the ax cosine bx, and so on. And the same for the sines. And let me finish off with a couple examples. So let's, oh, I don't have an animation on this one. That's all right. So if we have a mass spring system, so if we have a spring of, let's say, 1 kilogram attached to, if we have a spring and a 1 kilogram mass attached to it, and we squeeze it in a little bit, then we have some displacement distance. And when you squeeze it like this, then the spring obviously is going to push you back out, so you have some force. So now, by Newton's second law, force is equal to mass times acceleration, and if we let y be the displacement, then y prime is the velocity and y double prime is the acceleration. And it turns out when we put all these things together, you end up with the equation y double prime is equal to minus 4y by using Newton's second law. So I'm not going to go into too much detail on this because this is something that you would be learning in the physics class. But basically, once you put it in this form, well, then you can solve it using the differential equations models that differential equation techniques we have. So y double prime plus 4y is equal to 0. So that means lambda squared plus 4 is equal to 0. Lambda is equal to plus or minus I, and therefore y is equal to c1 cosine 2x plus c2 sine of 2x. So obviously this is the general solution. Well, what this means is that if you have some initial starting point, you're going to have something that is some combination of a sine and cosine. So maybe it looks something like this in terms of the position, which makes sense, right? Because if you have a spring, it's going to be oscillating back and forth, or oscillating up and down depending on how what way you're turning your frame of reference. And the other thing you can do here is you can solve the initial value problem as well. So the initial value problem is going to be where you have y double prime plus 4y is equal to 0, where you give an initial place and an initial velocity. So then, if we already solved this, so y is equal to c1 cosine 2x plus c2, c2 sine 2x, and we know that y prime is going to be equal to minus 2c1 sine 2x plus 2c2 cosine 2x. And when we plug this in, you get 10 is equal to y of 0, which is equal to c1 times 1 plus c2 times 0, which implies that c1 is equal to 0, and 0 is equal to y prime of 0, which is equal to minus 2c1 times 0 plus 2c2 times 1, which implies that c1 is equal to 10, and c2 is equal to 0. And you're left with y is equal to 10 times cosine 2x. And so the solution, if you start out at position 10, so if you've drawn out the spring to 10 meters, it's a really big spring, and you let go, you're going to get a solution that looks like this. Does anyone have any questions about all that? Okay, so that actually ends this part of, so basically we spent most of the last half of the lecture talking about what it meant to have complex exponentials, and in this part of the lecture we talked about how it means that you can take these complex exponentials and turn them back into a real solution, which is really important in biological applications because you don't actually have imaginary numbers of foxes or wolves or rabbits, but instead you want a real solution in terms of positive numbers often. Okay, and with that I will end this part of lecture, and we can have a brief couple-minute break, and then we'll go on to the next part of lecture. So let me stop recording now.